Hello everyone, my name is Weiyu. I'm from the University of Sydney, Australia, and today it's my great pleasure to introduce my work, namely Learning Early Exit for DNA Inference on Mobile Edge through Multi-Arm Bandits. So first of all, let me introduce a little bit of the background of my research. So over the past 10 years, we have witnessed the development of IoT. So starting from the cloud, which generated some big data, and then by utilizing this big data, which enhanced the AI and 5G technology, will also benefit the IoT and edge computing. So for the intelligent applications, we have facial recognition, virtual augmented reality, self-driving car, etc. And a lot of the times, some large deep neural networks are often used. Some of the challenges, however, we are facing now are those DNNs needs to be implemented on the mobile devices, and it requires real-time responses, which usually the case are very data and computation intensive. So that's why some previous study has investigated on the DNN's early exit. So here now we have a ordinary DNN model, but we have a number of early exit points that are added to this model so that we can exit the inference earlier without having to execute all of the layers of this model. By executing using earlier exit points, we can reduce the inference latency, but at the cost of inference accuracy. So finding the optimal exit point is challenging because there exists a trade-off between inference latency and accuracy, also because of the randomness of the system, where I'll get into in a second. As for the randomness of the system, our measurement suggests the following results. So we have two video input called scenario 1 and scenario 2. We have 3 exit points in the early exit model. So for each input frame, we record the confidence and latency of it, and the result shows that a huge variance difference between the confidence and a huge time difference between the time. Therefore, we need a new dynamic solution because it is impossible to predict the exact confidence and time of each exit point for each scenario. So here is an example of video inference during the service outage. So first of all, we sample a frame, which is frame number 1, and then we choose an exit point, which is the second exit point. After finishing this frame, we sample another frame, which is we also choose to use the second exit point. After we finish the second frame, we sample another frame, and then now this time we choose to use the first exit point. So that's how our system works. Whenever a frame is finished, we sample a new frame and decide which exit point to use. The goal of our study is to decide which exit point is the optimal exit point. Now let's come to the problem formulation. So we first say our problem is when the offloading is unavailable and the service outage time is unknown. Say we have L exit points in total, and each action represents the exit point that you want to use. So for example, if we use the action 2, we want to use the second exit point. And then by putting all of the action together, we have a action set A. And the action is chosen before the frame is processed. And then we define the expected values. So given we choose the A's exit point, the processing time and utility are IID. So utility here is a user-defined function of the confidence value. So now we define the reward of action A as the expected value of the utility divided by the expected value of the processing time, so that we can balance out the trade-off between the confidence and the latency. We define the optimal reward as the maximum reward among all of the exit points, and the optimal action is the action that can produce the optimal reward. Our goal here is to learn this optimal action on a per instance After that, we need to define observed values because due to the randomness of the system, it is impossible to know the exact number of the expected reward. So we define the observed processing time and the utility of the ice frame, and then we define the observed reward as follows. So now let's come to our Aoe scheme. So one of the techniques we are using for our Aoe scheme is multi-arm bandits, where we experience a trade-off between exploitation and exploration when we want to find the optimal action A. So the exploitation is when we always want to choose the action with the current best result by exploiting the best current result. However, the exploration is different from the exploitation, which is we want to explore new possibilities. So apparently those two things are contradictory to each other, so therefore we're facing this trade-off. One of the solutions is to use multi-arm bandits, which is in each trial, a learner can explore and exploit a set of arms, aka actions, to maximize its accumulated reward. So here come to the overview of our IE. First, let me explain the exploitation. So the exploitation means the average observed reward of taking action A, which is defined as the function below. And then let's come to the exploration, where we define a confidence radius. So from this equation, we can see that if the action A has chosen for many times, the confidence radius value decreases. Therefore, is less advantageous for exploration. Later, we will prove that the confidence radius can bound the deviation between the expected reward and the observed average reward. We then define the upper confidence bound and the lower confidence bound as the average reward plus and minus the confidence radius. So now let's see the trade-off between the exploration and the exploitation. So the larger the average value is, it means the action is good so far. So that is exploitation. And then come to the larger the confidence radius, the action needs to be explored more, which is exploration. So by combining these two together, we can balance off the trade-off so that we can select the action with the largest upper confidence bound, which is UCB. UCB is defined here. U equals to the observed average reward plus a confidence bound. So now let's come to our Aoe scheme. So here on the top, we are just about to sample frame I, and we want to make a decision for sample I. So what we are doing is we compute all of the upper confidence bound for all of the exits, and then we choose the exit point with the largest upper confidence bound so far, so that it can balance the trade-off between exploitation and exploration. And in this case, we just serve the purple frame, and then we possess the ice frame with the chosen exit point. So now we can see the LE scheme, the pseudocode on the right side, where we calculate, for each frame, we calculate the upper confidence bound, and then we choose the action with the largest upper confidence bound, and then we process the frame with this action. Now let's come to the performance analysis. Because we only have very limited time, so that we don't have enough time to go into detail for the performance analysis, but I will give you a quick introduction of it. So first, let me define the regret as follows, which is an accumulation of every time we're choosing the wrong non-optimal action, so that by by putting the action forward, we can see the equation as follows. So what we want to do to bound the regret is we want to bound the value in front. And then we just bounded the accumulation reward of all of the actions. So first, let me introduce lemma 1. So lemma 1, the purpose of it is to prove the event the lower confidence bound is the lower confidence bound and the upper confidence bound can bound the expected reward of an action. For all of the action and all of the frames, this event has a quantifiable high probability as follows. So here, for all of the action and all of the frame that this equation holds, this probability is very large. We proved this by using Hohenfinding inequality plus union bound. And then the expected reward can be bounded by the lower and upper confidence bound, so that we can know that when t is large enough, this probability is really high. And then let me come to the theorem 2. So theorem 2, by adding up all of the deviations introduced earlier, we can define the regret by this equation. It's no larger than this equation. And then by dividing by the overall time t, we can have the regret per unit is no more than this equation. So which means if t is sufficiently large, this value can approach 0. We can prove that this number asymptotically approaches 0 as t approaches infinity, so that we can prove the effectiveness of our. And now let me introduce to you our field experiment. So from the left is our testbed setup. So the video frames goes through our dashcam, and they are fitted into 4 of the Raspberry Pis at the same time. One has our Aoe scheme, and the other 3 has our benchmarks. And the whole testbed is deployed in a car where we drove through 3 of the tunnels in city, and the map is shown here. So when we drive through the tunnels, we lost the internet connection, so that all of the inference has to be carried out on the device only. When we drove through the tunnels, we record the input video, and then it is fed through to the Aoe scheme and 3 of the benchmarks. So here is the field experiment result. And first, on the left, we compare the exit point choosing for AlexNet internal A for the 30 seconds. So we can see the Aoe always choose the optimal exit point for the most of the times. And then on the right side, we have the percentage of choosing the optimal and second optimal exit point of 4 schemes in 6 cases. So we have 6 cases here, and Aoe is the teal color. We can see that the teal color is the most takes up most of the frames, which means Aoe chooses the optimal exit point most of the times in 6 of the schemes compared to the other 3 benchmarks. And then we come to the field experiment result 2, where we compare the accumulated reward of Aoe and the 3 benchmarks. Again, Aoe is the teal color, where we can see that Aoe has the largest accumulated reward in 6 cases, where it has the largest reward. We also carried out some simulation where the percentage of choosing, which shows the percentage of choosing each exit point, and the optimal and the second optimal are the 5th and the 6th exit point respectively. So here we can see that Aoe chooses the optimal exit point most of the time, while the benchmarks is less efficient compared to Aoe. Lastly, we also compare the accumulated sample path regret. So the lines here shows the average value and bars here shows the 75 percentile and the 25 percentile of each the result, and the data points are slightly shifted to avoid overlaps. So it is quite clear to see that LEE has the smallest accumulated regret compared to all of the benchmarks, and the variance is much smaller compared to the greedy algorithms. So in conclusion, first we have the mathematical contributions. We're the first to use multi-arm bandit to investigate on which exit point to use. We are facing two challenges. We have the confidence latency trade-off. We also have the random latency of each exit point. We mathematically prove that the regret of LEE asymptotically approaches 0. We also carry out field experiment and simulations. So we designed 2 new DM models with 6 exit points. We designed a real-time driving system where the testbed is mounted in a vertical, and we drove through 3 of the tunnels in Sydney with no internet connection. The result shows that we increased the accumulated reward by 55%, and also we prove that LEE can choose the optimal exit point most of the time. We also carried out some simulations, and the result shows that LEE can reduce the regret by 26.75% in average, and also we can choose the optimal regret most of the times. Thank you so much for listening to my presentation. If you have any questions, feel free to ask me after this presentation.